Now we're going to talk about some basic facts about combination numbers. Once we've learned how they're defined, let's look at some things that will make our life much easier when we deal with them. First thing I've kind of mentioned a little bit before, n choose k, this combination number, will be by definition 0 unless k is an integer from 0 to n. We don't want to talk about, in this class, 14 choose -1. What would it mean, a combination of length -1? We can't talk about 14 choose 15 because you can't have a combination of length 15 with distinct elements from a 14 element set. So this will only make sense if k is equal to 0, 1, 2, up to n. And you might ask, does it even make sense if k is 0? How many ways can you choose a combination of length 0 from an n element set? We'll kind of say that by definition, that's just one. There's one way to choose 0 people from a 30-person set. And we'll see that that actually makes sense with our formulas, because our formula that we had before was that n choose k is given by n factorial over k factorial times n minus k factorial. If k equals 0, we would have n choose 0 is just n factorial over 0 factorial times n factorial. And remember, 0 factorial is by definition just 1. So this is then equal to 1. So just as a standard definition, n choose 0 is 1. Well, what is n choose 1? There are two ways we could approach this. We could just plug it into the formula here, and I'll leave you guys to do that. What happens here when k equals 1? Or we could ask combinatorially, what does this represent? This represents the number of ways to pick a combination of length 1 from an n element set. Well, a combination of length 1 just consists of picking one letter. And clearly from an n element set of letters, there are exactly n ways to do this. What about n choose n? You have an n letter alphabet and you want a combination of length n. Well, it should be pretty clear that there is exactly one way to do this. Pick all the letters. Now here's a very important fact. All of these are true for any n. This, I claim, is true for any n and for any k, as long as, of course, k is between 0 and n. n choose k is exactly the same as n choose n minus k. So, for example, 5 choose 2, which we computed in our last video. That's just 10, the number of combinations of length 2. These are with distinct elements from a set of 5-letter alphabet. There are 10 ways to do that. What is 5 choose 3? Well, you could use this formula, or you could just think of 5 choose 3, and let me use this interpretation. 5 choose 2, remember, was the number of ways of picking 2 positions to put x's. I'll put x's here in a 5-letter string. 5 choose 3 is the number of ways to pick the 3 blank spots. And of course, these can be the same. Every way you pick 2 x's gives you exactly one way to pick 3 blank spots, namely the other spots. So these should be the same thing, 10. So one could make this argument, just do the same argument with picking x's. n choose k is the number of ways to place k x's in an n-letter string. n choose n minus k is the number of ways to place n minus k blank spots in a string with x's everywhere else. You can see that these two are the same. There's, of course, another way to see that this is true. n choose k. There's the formula for it, which says that's equal to n factorial over k factorial times n minus k factorial. If I just use that formula and try to compute n choose n minus k, that's going to be n factorial over, now I'll have n minus k here, n minus k factorial, and here I'll have n minus k factorial. And of course, n minus k is just k, and that's the same as n factorial over, this will be the k factorial here, and this will be the n minus k. factorial. So this is true for all n and k going from 0 to n. Here's going to be an important interpretation of combination numbers. N choose k is the number of subsets of size k from a set of size n. Let me show you an example of that interpretation. Let's say I have a set A, B, C, D, E, a 5-letter A, B, C, D, E. I said 5 and didn't write my E. I wrote 5. We have the set A, B, C, D, E, a 5-letter set. How many subsets are there of size 2? And we've already looked at this exact sort of question many times. 5 choose 2 is the number of 2-letter combinations. A subset of size 2 just is a subset with 2 elements. So here's an example of a subset, AB. When I write a subset AB, I could call that a combination AB. That clearly can be taken to be the same thing. You have other subsets, the subset BC, the subset with C and D, the subset with D and E. Anytime you have a pair of elements, they form a subset of size 2. So it should be clear that 5 choose 2 counts the number of subsets of size 2. How many subsets are there of size 3? Well, any combination of size 3 will have 3 distinct elements. Look at the subset that contains those 3 things. So this is just another interpretation of the combination numbers. Note that n choose 0 is the number of subsets of size 0. The only subset of a set of size 0 is the empty set, so this should be 1. So this choice that n choose 0 should always be 1 makes sense with this statement as well. Is it obvious that n choose n should be 1? Well, how many subsets are there of a set of size n, which themselves have size n? Well, the only subset of size n from an n-element set is the entire set. Now we'll ask the question, what is the total number of subsets of a set of size n? In other words, what's the total number of subsets of a set that looks like say A, B, C, D, E. I want the total number of subsets. The empty set is a subset. The set A is a subset. That's a 1-element subset. The set B is a subset. Other examples, the set A, B, E is a subset. The entire thing, A, B, C, D, E, that's a subset. There are many different subsets of this 5-element set. What is the total number? Well, let me show you a nice way to talk about subsets of a set. If you want to have a subset of the set A, B, C, D, E, you have to choose exactly which elements are in that subset. It might be none of the elements, it might be all of the elements, or it could be any smaller set of the elements. I'm going to look at a string, in this case a bit string of length 5. When I talk about a bit string, I mean a string of 0s and 1s. Here's an example of a bit string, 0, 0, 1, 1, 0. Any string that only contains 0s and 1s. How many bit strings are there? This is just from standard problem 1. There are 2 to the 5th, which is 32, such bit strings of length 5. 2 choices for each of the 5 positions. Now, there's a 1-to-1 correspondence between bit strings of length 5 and subsets of our original set A, B, C, D, E. For example, this bit string might correspond to the subset that contains C and D. the subset that contains only A would correspond to the bit string 1, 0, 0, 0, 0. The subset that contains B would be 0, 1, 0, 0, 0. The empty set would correspond to 0, 0, 0, 0, 0. ABE would correspond to 1, 1, 0, 0, 1. ABCDE would correspond to 1, 1, 1, 1, 1. There's this one-to-one correspondence between bit strings and subsets, and they're 2 to the 5th bit strings, so they're 2 to the 5th subsets of this 5-element set. In exactly the same way, we can see that the total number of subsets of a set of size n, the answer is 2 to the n, because we can make a one-to-one correspondence between bit strings of length n and subsets of an n-element set, and they're exactly 2 to the n bit strings of length n. Now, putting together what we've already learned, we get an amazing identity involving combination numbers, and that identity is this. If you add up the combination numbers, n choose 0 plus n choose 1 plus n choose 2, and go all the way up to n choose n, you get exactly 2 to the nth power. Why is that? Well, one can actually prove this in a variety of ways, but we'll give a combinatorial proof. That means a combinatorial argument that this is true. And the idea behind a combinatorial proof is you look at both sides of an equation and ask, what do these formulas count? Well, on the left side, we have the sum of these combination numbers. This counts the 0-element subsets of an element set. Here we count the 1-element subsets. Here we have the 2-element subsets, the 3-element subsets, all the way up to the n-element subsets. When I add those together, what do I get? I get all subsets of an n-element set, because every subset of an n-element set has either 0 elements, 1 element, 2 elements, up to n elements. So the total on the left should be the total number of subsets of an n-element set. Well, what about on the right? We just showed that this is also the number of subsets, the total number of subsets of an n-element set. And so they both count the same thing, so they must be equal. And this will be true for any number n equals 1, 2, 3, etc. It's also true even for n equals 0. So for n equals 0, 1, 2, 3, etc., this identity holds. Try writing that out. For example, when n equals 4, how many 0-element subsets do we have? Well, we know that that's just 1, because n choose 0 is always 1. How many 1-element subsets do we have? That's just going to be 4, because n choose 1 is always n. How many 2-element subsets do we have? Well, you might just play around with this a bit. So try to write them all down, or just use the formula, and you'll see that 4 choose 2 is 6. That's a good number to know. 4 choose 3, remember, has to be the same as 4 choose 1, and you can write them down directly. And of course, 4 choose 4 is always 1. Notice that's the same as 4 choose 0. And 1 plus 4 plus 6 plus 4 plus 1 is exactly 16, which is the same as 2 to the 4th. Try that for some other values of n, compute all the combination numbers, and you'll see that they sum to 2 to the n.